Good evening, students. Today we are going to discuss an important topic in grade 12 chemistry, coordination compounds. In that we will talk about ligands and nomenclature. First and foremost thing is, what do you mean by coordination compounds? Before we start, let us have a small introduction. We'll take some example of salts here. First one, you take NaCl. You can also have one more example, KBr. Now what will happen if you are adding water to this, that is aqueous solution of NaCl? This will split into Na plus and Cl minus. Here we can observe one cation, positive ion, and one anion. Now it lost its identity. NaCl in the solid state. Now you are having aqueous solution, in that you are having ions. You can test the presence of Na plus and Cl minus. That is salt analysis we can have here. So due to the presence of one cation and one anion, you can call it as a simple salt, or you can also call it as a normal salt. So this is one example. If you move to the second example, potassium bromide. In water what happens? It splits to K plus ion and Br minus ion. Again we can find one cation and one anion. Hence we can call it as a simple salt. Hope you have understood this, a very simple thing. So these particular salts are known as simple salts. So the first type what you have. The second one is, if you are checking out cornellite, Morse salt, potassium, etc. So first one what we discussed about the simple salts which contains only one cation and one anion. Next we talk about double salts, where you have two cations and then two anions. Hope you are able to understand. In the case of simple salts, one cation and one anion, but in the case of double salts you find two cations and two anions. First one, if you take KCl MgCl2 dot 6H2O, nothing but cornellite. Here once again, in the presence of water, or you add water, the solution contains K plus ion, Cl minus, Mg2 plus and 2 Cl minus, and then 6 moles water. So here we can again observe cations as well as anions with the presence of water of crystallization, so that will split up and you will be getting 6 moles water. So we can say that again this salt has lost its identity. You are splitting up this particular double salt into individual cations as well as anions, so you call this as a double salt. Now next one, if you consider dolomite, CaCO3 dot MgCO3, again in presence of water, you can easily understand here Ca2 plus carbonate anion, Mg2 plus carbonate anion. Once again you can see two types of positive ions, that is cations, and two different anions. Hence you call it as a double salt. Again it lost its identity, and you can check out the presence of these ions using salt analysis confirmatory test. So this is also an example of a double salt. So we can have some more examples. Potash alum you take. What is the formula for potash alum? Potash alum, if you take potassium sulfate, aluminum sulfate with water of crystallization, that is 24. Again, if you dissolve it in water, that is in the aqueous solution, what you find 2K plus, here SO4 2 minus, then 2Al 3 plus ions and 3 sulfate ions plus 24 water molecules. Hope you are able to understand this. Once again, it lost its identity in the aqueous solution and you got the respective cations as well as anions. So two types of cations as well as anions, hence you call it as a double salt. So we understood what is meant by a simple salt and what is meant by a double salt. Now the third one, a complex salt. So here this will give us introduction about the coordination complexes. We call this as coordination compounds as well as coordination complexes. So if you understand the third one, we can enter into our topic, complex salt. So we don't want to name as such. First let us see cuproammonium sulfate, then K4FeCN6. Here you can see that I have written the square bracket. So this square bracket, I'll tell you what you call that. It is called as, here you call it as a complex ion. So what is meant by a complex ion here? Once again, add water to this. So it's a reversible reaction here. So you will be getting CuNH3 twice. So here it will be 2 minus, hence it will become 2 plus. So it is called as a cationic complex, and this you can call it as a complex salt. So what is happening here is, this complex ion does not lose its identity, it retains its own identity. That means you cannot split it further into Cu2 plus or you cannot split it into NH3. But the one which is present outside the square bracket, it is nothing but, you call it as a counter ion. You can test the presence of only sulfate here. So if you add barium chloride to this, you will get a white precipitate of barium sulfate. So you can identify sulfate ions, but you cannot identify the presence of copper ions or the NH3 ions. So here this is a very simple thing. A complex ion does not lose its identity in aqueous solution. Similarly, here you can identify 4K plus FeCN6. Here you can say this is 4 plus, hence it will become 4 minus. Hope you are able to understand. This is a cation. Now you can call it as anionic complex. So once again you can find out the presence of K plus. So here salt analysis, if you perform, you can get the presence of this using picric acid, yellow color precipitate you will get. But this one you cannot identify the presence of iron as well as cyanide ions. So because this is written in the square bracket, you can say that it's a complex ion. Due to the presence of negative charge, you call it as anionic complex. Now let us see what is the individual thing. That is, if you consider copper, what do you call that? What is meant by NH3 here? Now you know that here this is called as a counter ion. So K plus is positive counter ion. This is an anionic complex. In that, Fe will be the central metal atom and Cn minus will be your ligand. So we will talk about what is meant by ligand now. So we have three types of complexes. I'll just represent MLX0, MLX plus, MLX minus. So what is M here? M is nothing but central metal atom or ion. So where M represents central metal atom or ion, here you can say Cu. NH3 is a ligand here, represented as L. What is meant by a ligand? L stands for ligand. Once again, ligand can be classified as neutral ligand. Example, you have NH3, there is no charge, but you have one lone pair of electron. So ligand is nothing but an atom or group of atoms or ions which will donate a lone pair of electrons to the central metal atom. Now if you can also have anion or negative, so F minus, Cl minus. Now here you are having Cn minus, so these will come under negative or anionic ligands. Positive or cation, so hydrazinium, so NH2, NH3 plus you can get. So this will be rare, but mostly you observe neutral as well as anion. So ligand is nothing but which donates electrons, that is lone pair of electrons to the central metal atom or ion. Now here I have taken X. What is meant by X? X is nothing but the number of ligands. X indicates number of ligands, and here 0 is nothing but neutral complex, plus is nothing but cationic. Just now we have discussed this will be cationic, you have 2 plus. So this Cu is 2 plus, this is 0. Now minus is nothing but anionic complex. So we have 3 types, that is MLX to the power 0, it's a neutral complex, second one cationic complex, third one is anionic complex. So here if I want to explain Fe, first to find out what will be the oxidation state. So take it as X, Cn is minus 1. So we can write like this, X minus 6 is equal to minus 4. In the redox reactions we have discussed how to calculate the oxidation state. Same method I am applying here. Send 6 to other side, X is equal to minus 4 plus 6 nothing but plus 2. Therefore Fe will be plus 2. The central metal ion is Fe2 plus here. And the ligands are nothing but Cn, cyanido. We will discuss about that later, names and other things. So here we have 6. So if you want to write, you can write like this, MLX minus negative, in that M is Fe2 plus, L is Cn minus, and X is 6 here, number of ligands, and negative charge, that is 4 minus. Hope you have understood this. Here if you want to write, this is M. Now L, how many are there? 2, X plus MLX plus you will get M is Cu2 plus, and ligand is NH3 amine, X is 2, and the charge is 2 plus here. So cationic complex as well as anionic complex. So if you take nickel tetracarbonyl, so nickel tetracarbonyl we have discussed cationic, we have discussed anionic. Now if you take neutral one, what is central metal atom here? Nickel. Nickel we can write it as M here. M is nickel. Now ligand is CO carbonyl, and if you observe here the charge is 0. What is the reason? Because the ligand carbonyl has got that is neutral ligand, so 0. Nickel is also 0. The total is also 0. So we can write like this, MLX here to the power of 0, or MLX 0. Neutral complex, metal is nickel, ligand is carbonyl, X is 4, total charge is 0. So this is nothing but a neutral complex. Now the compounds which we are discussing in this way, that is they show the coordination bonding. So we know what is meant by coordination bonding. The ligand, by donating the lone pair of electron, forms a bond with the central metal atom. So we discussed this in detail. Before that, let us talk about ligands and the types of ligands. Hope you have understood up to this. Next, let us talk about the oxidation number of the central metal atom or ion. First one is cuprammonium sulfate. You have to find out Cu. So let us take it as X here. Sulfate is 2 minus. You call it as contra ion, or you can also call it as ionization sphere. Ionization sphere, this one. So here we have 2 plus. NH3 is neutral ligand, hence we put it as 0. Now I will calculate this. X plus 4 into 0 is 0 is equal to plus 2. Therefore, X is equal to plus 2. You can write it as Cu plus 2 R2 plus. Hope you have understood the first one. Second one, they have given minus 3 and cyanide Cn minus 1, Fe is x. While calculating, we take it as x plus 6 into minus 1 minus 6 is equal to the charge on the anionic complex is minus 3, so we have taken like that. Send minus 6 to other side, what we get? X is equal to minus 3 plus 6, therefore x is plus 3. We can write like this, Fe is plus 3 or 3 plus. Hope you have understood this, Fe 3 plus. So the oxidation number of Fe here is plus 3. Next, AuCl4, this is minus 1, take it as x minus 4 is equal to minus 1, send minus 4 to other side, x is equal to minus 1 plus 4, therefore x is equal to plus 3. Au we can take it as 3 plus or plus 2. Hope you have understood the calculation of oxidation number. Next, Ni, CO neutral ligand, take it as x plus 0. So here we 4 into 0 is 0, total charge 0, therefore x can be 0 and we can write nickel 0, oxidation number is 0. So this is nothing but a neutral complex. Neutral complex. Hope you have understood this, very simple. Now if you are talking about this, for example, if I take Au, so we have 3 plus charge and ligand Cl here, 4 are there, Cl minus 1 donating 1 pair of electron, so this is Cl minus 1, another Cl minus 1 and the fourth one Cl minus 1. This is the complex here, coordination complex, wherein this is called as a ligand. This is central metal ion. So we need to calculate the oxidation number and then we can write the geometry of that. Later we will know how to calculate that. First and foremost thing, we have done the calculation of oxidation number of central metal atom or ion. Next we will see the types of ligands. First one is, we will see depending upon the charge on that, the ligands can be of 3 types. So number 1, it can be neutral, it can be positive or it can be negative. Let us discuss in detail. Now on the basis of charge, we have classified ligands into 3 types. You know what is meant by a ligand? A ligand has lone pair of electrons and it will donate that lone pair to central metal atom or ion by forming the coordinate covalent bond. Here H2O, we have oxygen with 2 lone pairs. It is neutral, hence we consider it to be in the first case, that is neutral ligand. No charge on this. Next, amine. NH3 have nitrogen with 1 lone pair, carbonyl oxygen with 2 lone pair of electrons. So carbonyl group CO. If you have negative charge, those are called as anionic ligands. Example, fluorido, chlorido, bromido, acetato, cyanido, hydroxo. We will write the names in the second type of classification. Here you have negative charge on the ligands, they will be donating this pair of electron. Coming to cationic ligands, which have positive charge, nitroselium, these are rare in case, so NO plus, hydrazinium, that is NH2 NH3 plus, so they are rare in case, wherein you can also donate the lone pair from nitrogen. Here also we have one lone pair. Hope you have understood this. Now on the basis of charge, we have 3 types. Second one is on the basis of donating atoms, that is number of atoms, we can write it as unidentate, didentate, tridentate and hexadentate and so on. So let us write the examples for that. Next, second type of classification on the basis of number of donor atoms. If the donor atoms are 1, you call it as unidentate. Donor atoms 2, 3, 4, 5, 6. So unidentate, didentate, tetradentate, pentadentate and hexadentate. First one, let us talk about unidentate ligands. What is the meaning of this? Unidentate means the number of donor atoms here donor atoms here is one, only one donor atom, that is only can have one ligand here. Examples, let us see. First one, if you take, it can be neutral or negative. If you talk about neutral ligand, here what is the donor atom here? Oxygen. Oxygen is the donor atom, only one atom is there. It can donate either this or sometimes both. You call it as aqua, AQUA. Name also we have to write like this, aqua. Second one, NH3. Here nitrogen is the donor atom, only one. You call it as amine, AMMINE. We need to write 2M here. Fine. Next. If you talk about the negative, F minus, Cl minus, Br minus, I minus. This is called as fluorido. Cl minus, chlorido, the name of the ligand. Br minus, bromido. I minus, iodido. Hope you have understood this. It ends with IDO here. Next, you know pyridine. If you want to write aromatic ring, so we have C6. I can write like this, then pyridine. So in this condition, we can take C5, H5N, where N is having one lone pair. So this is also a unidentate ligand where nitrogen is the donor atom. So this is called as pyridine. C5H5N. You can write a PY, nothing but pyridine. Hope you have understood this. Now coming to the next examples. Cn minus, OH minus, NO2 minus, ONO minus, SCN minus, NCN minus, CH3COO minus, NH2 minus, last one is NH2 minus. I'll write the names here. Cn minus, we should not write cyanide, we have to write it as cyanido. OH minus is called hydroxo. NO2 minus is nitro. See, now the position is changed. We will discuss in the isomers about this type. ONO minus nitrito. Next, HCN minus thiocyaneto. But if you put NCN minus, NCS minus, here N is the donating, here sulfur is the donating atom. So isothiocyaneto, this is the name of the ligand. Now CH3COO minus, you know, acetate ion, but here you have to call it as acetato. The ligand is acetato. NH2 minus is nothing but amino. NH2 minus is amido. Sorry, imido. So hope you have understood this. These are called as the first type unidentate ligands where the number of donor atoms are only one. So in the next class we will discuss about the remaining ligands with the examples. Hope you have understood this. So thank you so much.